Okay, this is atomic and nuclear physics. It should take around 2 hours, and we should be able to make the main points in about 10 or 15 minutes. First of all, this is a model of the atom from the turn of the 20th century. It's called the Rutherford atom. We have the nucleus, which contains the protons and neutrons, and we have orbiting the nucleus the electrons. They're attracted to the nucleus by the electrostatic attraction between the electrons and the protons. This is the Rutherford model of the atom. How do we know we have a nuclear atom? In other words, an atom which has a concentrated, dense nucleus. This is the earlier model of the atom. It was believed that the electrons, which are able to move freely around, were like current buns floating inside this current bun, and the positive was this doughy stuff here. So this was the idea. We had a kind of a doughy positive charge with electrons which were moving around this way. So this is called the plum pudding or the current bond model. Okay, so the electrons were detachable, were able to move around, and these carried the negative charge. And the doughy stuff was the positive stuff, which is what carried the positive charge. So, okay, so Geiger and Marsden, under Rutherford's supervision, did an experiment which basically proved that this was not the case. What they did was fired helium nuclei, which are alpha particles, very positive, compact particles, at a thin gold leaf. So these particles were supposed to cut through this doughy positive entity and come out the other end. So they expected all of the particles just to go through unaffected, because they just cut through the doughy positive part like a knife through butter. So they expected the particles just to cut right through. But what actually happened surprised them. Most of the particles did cut right through. Most of these positive particles did cut right through as expected, but some were deflected by quite considerable angles, and some actually bounced back. Now that shouldn't happen. If you throw a knife at a loaf of bread, you don't expect the knife to bounce back. You expect it to cut through. So the model was not a good one. Now we understand now that the reason that they bounce back is because the positive charge was actually in a very compact center of the nucleus of the atom, called the nucleus. That's where all the positive charge was concentrated. So that's why these other particles came back. Most of the particles were not deflected at all, because most of the atom is space. Some that approached fairly close to the nucleus were deflected by a small amount, but most of them were not deflected at all. So here we go. The observation is this. Nearly all the other particles went through without deviating. That was what would be expected. Some, however, some particles were deflected quite considerably and even bounced right back. This was not expected. So what is the explanation for the first point? We expected this to happen. So the conclusion from this is that most of the atom is made of space. In other words, there's not enough repulsion. There's no matter repelling the other particles. However, the only way that some could be deflected or even bouncing back would be if all the positive charge were concentrated in a very, very dense, compact nucleus. And this is how we ended up with what's called the nuclear atom. So, the limitation of this nuclear atom. The nuclear model was that the electrons were orbiting the nucleus, a bit like planets orbiting the sun. And whereas the planets can orbit at any distance they like, it appeared that the electrons only were allowed to orbit in certain distances. At certain distances, only certain orbits were allowed, and there's certain places where you might expect the electron to be, the electron wouldn't exist there. So only certain electron orbits were allowed. So what is the evidence for these atomic energy levels, these orbits of electrons? Okay, you need to be fairly familiar with the emission and absorption spectra. Light is not a continuous wave, but emits packets or photons of energy. Each packet of energy has an energy. Each packet of light each photon has a packet of energy which is equal to hf. So, what is a continuous spectrum? This is when we have light, which is of an object which is glowing so much that it's emitting in all parts of the spectrum, from the red to the blue parts of the spectrum, and it's a continuous spectrum. If this light, however, were to go into an area where there is a gas, so what happens is that when you see this continuous spectrum, some lines are missing. Some lines are missing here. As we know, each frequency corresponds to a certain energy. E is equal to hf. So it corresponds to one amount of energy that's been absorbed. This is another piece of energy that was absorbed. Nothing was absorbed here or here, but there was an absorption here, an absorption here. And the interesting thing is that when you observe it not straight on here, but from an angle, we saw some emission at an angle which is along the line that was absorbed here. So this energy is being absorbed from the continuous spectrum and then re-emitted. And you can see it at another angle. This energy has been absorbed, then re-emitted. This energy has been absorbed, then re-emitted here. And these are the emission lines. So we have this ionized gas which absorbs certain frequencies and then re-emits them. So only certain frequencies are re-radiated, and only certain absorption lines, which correspond to these re-emission lines, exist. So what is an explanation of this? Light, photons and absorption spectra. Inside an atom there's a ladder of allowed energy levels. Like this is allowed, energy 1 is allowed, energy 2, energy 3 and energy level 4 is allowed. So it's like rungs on a ladder. So what we're going to do is the light comes in, which has a certain packet of energy which is just enough to give this electron enough energy to go up to a higher level. So this packet of energy, this photon, gives exactly the right amount of energy for electron to go to a high level. These photon energies are equal to the energy transitions between the levels. So what we're going to see is this. The photon comes in, which is exactly the right energy, and is going to make the electron go from here to here. Let's see that again. There's a whole range of light is coming into this atom, but only one frequency is going to be absorbed, and that corresponds to this energy jump. So this photon of energy has given the electron enough energy, just enough energy, to go from the level E0 to E3. So it's this energy difference which is important. So this change of energy, which is energy of E3 minus E0, will be the energy of the photon, E is equal to hf. You have to understand the terms nuclide, isotope and nucleon. What is a nuclide? A nucleus with a specific number of protons and neutrons. So this is a nuclide. When you decide which atom it is, you define the number of protons and neutrons. That's just a general term for this, a nuclide. A nucleon is the name of the particle which exists in the nucleus. That's why it's called a nucleon. So we have protons and neutrons. These are nucleons. So it's a nuclear particle. An isotope is an element which is defined by the number of neutrons that it has. So you might have different isotopes of the same element because it has a different number of neutrons. For example, carbon-12 has 6 neutrons. Carbon-14, which is still carbon, has 8 neutrons. It's the same element, but it has a different number of neutrons, and therefore it is a different isotope. Define nucleon number A, proton number Z, and neutron number N. The nucleon number is the number of nucleons in the nucleus. the proton number Z is the number of protons in the nucleus. The neutron number N is the number of neutrons in the nucleus. Now we know that the protons and the neutrons add up to the number of nucleons. In other words, A is equal to Z plus N. Describe the interactions in the nucleus. We have basically two of the most important ones in a stable nucleus. There's the Coulomb electrostatic interaction between protons and the strong nuclear force, or the strong, which is a short wave nuclear interaction between the nucleons. So between each proton there's this electrostatic repulsion, and there's an attractive force, which is the strong nuclear force. Now the nucleus has a tightly packed neutrons and protons, and we know that protons are all positive, so there's a huge repulsive force between the protons. So these forces repel. So really the nucleus should explode because the repulsive forces are so great. But there must be another force, which is even a stronger force, which is keeping it together. Now there's a force called the strong nuclear force, which acts only at very, very short distances inside the nucleus. So far we know of the electrostatic forces and gravity, so there's a new force which exists only in the nucleus. So it's a new fundamental force, and we'll find out a little bit more about that in the next topic.